Hi guys, welcome to our third video of the computer lab session. In last video, we used the LM function to fit the linear model, and then used the summary function to generate the regression output. And recap the regression result. We see the coefficient estimate of the intercept and the excessive return of the market portfolio is slightly greater than 0 and 1 respectively. In the context of CAPM, if the population parameter of the intercept is greater than 0, we say that it outperformed the market. And if the true population parameter of the excessive return of the market portfolio is greater than 1, we say that the risky security is an aggressive asset. But is it sufficient for us to conclude that like the IBM is both outperform the market and also an aggressive stock? It's unlikely, right? Like we are not sure about it yet, as the coefficient estimate are random variables and they are estimate of the unknown parameters and will vary from sample to sample. We illustrate it by excluding one observations from the sample, and you'll see that like even excluding the sample range or including more sample range, will the coefficient estimate will fluctuate from sample to sample. So just for illustration purpose, we'll run the LM function again, but this time excluding the first observation. And if we compare the coefficient, the regression result, we see that like it doesn't drastically change the coefficient estimate, but still it fluctuates from sample to sample, right? So in order to make any meaningful conclusion, we need to use hypothesis testing. So yeah, let's start with a two-tailed test. Let's start with a two-tailed test and see whether IBM has abnormal returns. In other words, we are going to test the null hypothesis that the intercept is equal to 0 against the alternative hypothesis that the intercept is not equal to 0. So we will start with the approach that compared the test statistic against the critical value, and as we are asked to test whether IBM has abnormal return. So the hypothesized value in the context of CAPM is going to be is going to be 0, right? So in fact, we can actually use the t value reported in the by R automatically, but to illustrate, we'll compute the t value by ourselves, as you encounter a different hypothesized value in the next cases. So first of all, we are going to save this this matrix and name it as coefficient and as something like this. Like you can change the name you want, but I will just put it this way. And then and you can see that it is essentially just the matrix itself. So to calculate the test statistic, we are going to need the coefficient estimate of the intercept and the standard error of the intercept. So which is first row column 1 and first row column 2. So we just name it as beta intercept and standard intercept, standard deviation intercept. And then hypothesized value we set to equal to 0, and then we can calculate the test statistic. So if we just print out, it's actually exactly the same as the one reported by R, and it worked only this case because the hypothesized value is also 0. And I have to repeat again, like if you have different hypothesized value in other hypothesis testing case, you will need to calculate the test test statistic by itself. But in this case, you could simply extract it, say the first column and the first row and third column, which is exactly the same thing as we compute by ourselves. So yeah, alternatively, you can just copy and paste, but I don't recommend that. Like it will, because it is there might be rounding issue, and also you might accidentally include less than what you need. Yes, we compute the test statistic, and let's get the critical value of yeah, because this is a two-tailed test for with the 5% significance level, right? So each side is going to be 2.5%, and essentially we want to calculate the threshold that give the CDF of 97.5%, and this is wait. Actually, I should include this. Like I will put the I will put a video that that explain the distributions, optional video in the regarding distribution at the end of the watch list, and it's basically that like for every distributions, for every well-known distribution in R, like they have common functions. They have built-in functions for common actions, like how to compute the density, CDF, quantile, and also a function to generate random numbers for that distributions. So in this case, like these actions are represented by D, P, Q, R, and then attached with the distribution symbol name. And in this case, we want to calculate the critical value of the T distribution with like with the 97.5% probability, and the degree of freedom in this case. Sorry, I have to check again. Is the degree of freedom is 196 degrees. So we provide the probability as the first argument, which is 97.5% in the two-tailed test, and 196 degrees as the degree of freedom, and we compute the critical value, which is no surprise because like it is quite popular, and then we will which is quite close to the critical value compute using the standard normal distribution, and then we will we'll compare against the the absolute value of the test statistics, and as the absolute value of test statistic is 0.22 something, right? It is not greater than the critical value that we just calculate, and in this case, we cannot reject the null hypothesis, and therefore we can't conclude that like we cannot conclude that the IBM has abnormal returns. And in second, a second approach that we can do is the p-value approach. It's like we can calculate the probability of observing a test statistic that at least as different from 0 as the value from the test statistic actually compute from the sample. So in this case, we are going to compute the 1 minus CDF, like the PT is actually calculating the like if we let the lower dot tail equals to true, as by default is going to compute the CDF. But if we set it to be a lower dot tail equals to false, we are actually computing the survival functions. Yeah, if we set it equals to false. So in this case, we are going to set it to false, and then we are going to compute the shaded area of the of the right side, the shaded area of the right tail, and we provide the test statistic, and then we provide the degree of freedom on the second arguments, and then we set the lower dot tail equals to false. So now we calculate the test statistic, and then as the not the test statistic, we calculate the right hand side of the rejected region, and by the explore the symmetric property of the t distribution, the shaded area in the left side is equals to the right side. So we just simply times 2 to get the p-value, and we see that the p-value is 0.8226, which is way larger than 0.05, and therefore we cannot reject the null hypothesis that the population parameters is the parameter of the intercept is equal to 0. In that case, we cannot say IBM has the abnormal returns.